Hey there, and welcome. Have you ever looked at a chemical name and felt like you were trying to read a secret language? Well, you're not wrong. But today we are going to crack that code. By the end of this, you'll have the key to figuring out how scientists name literally millions of different substances. So let's get started.
All right, let's just dive right in with the puzzle. Take a look at these two formulas, NaCl and CuCl. I mean, they look almost identical, right? You've got a metal and you've got chlorine. But one is just called sodium chloride, and the other one gets this weird Roman numeral, copper I chloride. What's up with that? Why the different rules? This little bit of confusion is exactly what we're going to clear up right now.
Believe it or not, this entire system, which seems so complicated on the surface, really just boils down to answering one single, simple question about what a compound is made of. And here it is, the big question. Does the compound have a metal in it? That's it. Your answer, yes or no, is the fork in the road. It sends you down one of two totally different naming paths, each with its own set of rules. This flowchart just perfectly lays it all out. See that very first split at the top? Metal present? If you say yes, you go down the path for what we call ionic compounds. If you say no, you follow the rules for molecular compounds. Making this one decision correctly is, without a doubt, the most important step. So here are the two big families of chemicals we're talking about. On one side, you have ionic compounds. This is your metal plus nonmetal combo, where electrons are literally transferred, given away. On the other side, you have molecular compounds. That's when two nonmetals get together and share electrons. And this fundamental difference, giving versus sharing, is the whole reason we need two different ways to name them. Okay, so let's explore that first path, the one for compounds that have a metal. We're in the world of ionic compounds now, and the whole story here is about the give and take of electrons.
So what is an ionic bond really? Well, it's when a metal atom just gives one or more of its electrons away to a nonmetal atom. Now, since the metal atom lost a negative electron, it becomes a positively charged ion, we call that a cation, and the nonmetal, which just gained an electron, becomes a negatively charged ion, an anion. And you know what happens with opposites? They attract. They snap together like tiny magnets. Let's make this real with a classic example. Over here, we have sodium. It's a soft, super reactive metal. And on the other side, we've got chlorine, a poisonous greenish gas. Honestly, by themselves, they're both pretty nasty characters. But here's where the magic happens. The sodium atom hands over an electron to the chlorine atom. Suddenly, you have a positive sodium ion and a negative chloride ion, and they lock together into this really stable, beautiful crystal structure. And what is this new thing? It's just table salt. Totally harmless. A completely new substance, all from that one little transfer. Now, naming this stuff is so simple, it's beautiful. First, you just say the name of the metal, sodium. Then, you say the name of the nonmetal, but, and this is key, you change the ending to "ide." So chlorine becomes chloride. Slap them together and you get sodium chloride. See? Easy. Okay, sounds simple enough, right? But this brings us right back to our original puzzle. What do you do with those other metals? You know, the ones in the middle of the periodic table that are a little less predictable. The ones that can give away a different number of electrons and end up with different charges. And this is exactly why it matters. A metal like copper can form a +1 ion or a +2 ion. If we just said copper chloride, how would anyone know if we meant CuCl or CuCl2? Those are two completely different things. In science, that kind of ambiguity is a huge problem. So we need a solution. And that solution is Roman numerals. So here's the rule. If a metal can have more than one possible positive charge, you have to tell us what that charge is using a Roman numeral in parentheses. That's why CuCl is copper 1 chloride. The copper has a +1 charge, and CuCl2 is copper 2 chloride, because that copper has a +2 charge. Now, just remember, you don't do this for everything. The metals in groups 1 and 2 are predictable, their charge is always the same. Same goes for a few common exceptions you should just memorize, like silver, zinc, and aluminum. For those guys, no numeral is needed. All right, let's rewind and go back to that fork in the road. What happens if our answer to the big question is no? No metal present? Well, then we head down a whole new path, the world of molecular compounds, where it's all about sharing. See, in these compounds, you get what's called a covalent bond. Instead of one atom stealing an electron from another, they cooperate. They share electrons to stick together. forming these little self-contained packets called molecules. Think of things you know, like water, H2O, or carbon dioxide, CO2.
Now, the thing about nonmetals is they're super flexible. They can combine in all sorts of different ratios. So we need a system to be very, very specific about how many of each atom we have. And to do that, we turn to some handy Greek prefixes to help us count. The rules here are also super systematic. You name the elements in order, and you use those prefixes to say how many. Now, here's a little quirk you got to remember. The first element only gets a prefix if there's more than one atom. That's why CO2 is carbon dioxide, not monocarbon dioxide. But for the second element, you always use a prefix. So N2O is dinitrogen monoxide. And yep, just like before, that second element's ending still changes to -ide. So we have these two totally separate sets of rules, one for giving electrons, one for sharing them. But why is this so important? Well, because this whole naming system, which we call nomenclature, is the universal language of science. It means that copper 2 chloride means the exact same thing to a chemist in Tokyo as it does to one in Brazil. And the reason this all works is because of a fundamental law of nature that a chemist named Joseph Proust figured out way back. The law of definite proportions basically just says that a pure compound always has the same recipe. Pure water is always H2O, 2 hydrogens, 1 oxygen, always. And because that recipe is fixed and reliable, we can give it a name that's just as fixed and reliable. And what's really cool is that this system is powerful enough to handle even more complex stuff. Sometimes you get these little teams of atoms that stick together and carry a charge, acting like a single unit. We call them polyatomic ions, things like ammonium or nitrate here. We don't have to panic. We just treat the whole group as one piece and use the exact same ionic naming rules. So a compound made of NH4+ and NO3- is simply named ammonium nitrate. So why do we care so much about getting the name right? Because the right name gives you the right formula, the recipe. And with that recipe, you can do actual important chemistry, like calculating a compound's molar mass, a vital piece of information. As you can see, you just use the formula to count up the atoms, look up their weights on the periodic table, and add it all up. This calculation, which is done in labs every single day, is only possible if you start with the right name. So there you have it. The entire massive system of naming compounds all comes down to one question. Is there a metal? From there, a logical path of rules takes over, whether it's for transferring electrons or sharing them. This isn't just about memorizing stuff. It's about understanding the language that matter itself speaks. So the real question is, now that you have the key, what other chemical codes are you ready to crack?